Hi, welcome to State Space Modeling with Tim. In this video, we're going to cover how to convert transfer functions that are in the form of R of S over P of S into state models, where R of S and P of S are polynomials in the frequency domain such that S is equals to j omega. In the previous videos, I introduced a step methodology to converting transfer functions into state models, and those steps, 5 of them, are shown here below. I'm not going to go over them again, but you can pause the video or go to the previous videos to see how these steps were derived and how they've been used in other examples. So without wasting any time, let's start off with the video. So I've decided to teach this particular procedure for transfer functions that are in this rational function using an example. So again, we're going to be going over the 5 steps. We're going to use those 5 steps to solve this problem, but I will be trying to point out what are the implications of, in particular, the numerator and the denominator in terms of how our state space model is going to look like. So let's begin with the problem. So usually, as you may have seen above, in the step 1 is when we actually try to rationalize, but before we can actually start with step 1, I would like for us to look at the control block diagram of this transfer function system. So let's look at the block diagram. Okay, block diagram. And I'm going to try to draw it in red. So first of all, we should define that h of s, the transfer function, we know that it's a ratio of the output over the input. And I'm going to define the input as u of s and the output as y of s. So I'm going to say this is the output and this is the input. This should be something everyone is familiar with. Okay, so now we can draw a block diagram in terms of y of s and u of s. So on the left hand side, we're going to have our input, and I'm just going to copy this so that we don't waste too much time. And then on the output, we're going to have y of s. So this is what a simple control block diagram of our transfer function should look like. Okay, so this is what we've been working with from the beginning when we started looking at transfer functions and converting them into the state space model. So the next thing I want to do is I want to display this block diagram in a way that we've already worked with before so that it makes things much easier for us. So what I'm going to do is I'm going to try to expand this control block diagram, and I'm going to break it apart such that we can have the denominator and the numerator separated, and we're just going to be using, without violating our rules of control block diagrams. In fact, we're just utilizing those rules to make this happen. And we'll see 24, and this is going to be over 1. And those of you who are experienced in control system, you should be able to recognize what's happening here. And I'm going to separate both the numerator and the denominator so that we have two blocks. 7s plus 2. And then we still have the output here. And here, because now we have 2 blocks and so we should have an intermediate system here. And I'm going to define this intermediate as m of s, m representing middle. Okay, so this still means the same thing as our initial block diagram. I hope that is obvious for everyone. Okay, so what can we say now? We can now use our 5-step model again to solve this problem here, but we can break it down into 2 parts. So we can use the 5-step model twice. So I'm going to label this section in green as part 1, and I'm going to label this section as part 2. And I hope this will be easy to follow for everyone. Okay, so one worth noting is that part 1 now has m of s over u of s. And that's going to be the transfer function there of part 1. And now part 2 will have y of s over m of s. Remember, the transfer function is just a ratio of the input of the output over the input, or to the input. Okay, so without I think now doing that, we can start off with part 1. So part 1. So part 1 is again m of s over u of s, which I strictly remember it just being the denominator, which was s cubed, or we can just go scroll up and see s cubed plus 9s 26s. Made a mistake here, can be rectified, and we can continue. So that's going to be 9s squared plus 26s plus 4. Oh, plus 24. Sorry about that. Okay, so now we can go with our steps. And step 1 was that we must first linearize this transfer function so that we can be able to apply the inverse Laplace transforms. I'm just going to use the blue pen. So if we cross multiply here, what we're going to have is m being multiplied by s cubed plus 9s squared plus 26s plus 24, which is going to be equals to u multiplied by 1, which was our numerator on the right hand side. Okay, and now we can move on to step 2. And step 2 says we take our inverse Laplace transform. So if we take the inverse Laplace transform, and I'm just going to copy this again because it's so much easier to do that, and I'm going to bring out, oh, I thought it had been copied. I don't know what happened. I'm going to copy this down here. I select it, yeah, and then we're going to take red, and then we're going to take the inverse Laplace transform, which is that of this whole thing. I don't think this is symbolically correct. I don't think you should do this. I'm just writing it to make things a bit more simpler and quicker. Okay, then we're going to go back to blue. So what we get here is going to be the third derivative of m dt3 plus 9, the second derivative of m with respect to time, plus 26, the first derivative of m, not y, plus 24 m, and on the right hand side we get u. Okay, so, and I should point out that m is just equals to m of t, which means m as a function of time, because we've just converted from the frequency domain to the time domain. And u is also a function of time, for those that it wasn't clear for. And remember, what we just did here is we took the inverse Laplace transform. So I think I should point this out. This is the inverse Laplace transform. If this is a bit confusing, remember that for the inverse Laplace transform, we say that for s to the power of n of a function, in this case y of s, the answer is just the nth derivative of our function with respect to time. So that's what we just did right now. Okay, so now we can move on to the next step. And before we can actually move on to the next step, I wanna, for those who have been following this series, we know we're gonna have to isolate this. So I want to make this the subject immediately here before we move further, so that we can use it later without having to do this all over again. So I'm just gonna make this the subject, So it's just a bit of rearranging, and I'm gonna try to start from here and do that. And so we get minus 24m minus 26 dm dt minus 9 d squared m dt squared plus u. So nothing magical, we just moved from here to there, so we just rearranged here by making I can call it m dot dot the subject, the third derivative of m. Okay, so we're gonna use this equation, this differential equation a bit later. So I just wanted it to be ready for us when we need it. Okay, so now we can move to step 3. And that is we define our phase variables. Okay, so like we said, phase variables are identified by the variable that is being differentiated with respect to time. And the only variable that's being differentiated with respect to time in our differential equation is m. So we can say, and I'm going to try to go back to blue now, let x1 is equals to m, and then we can say let x2 equals to the first derivative of m with respect to time, and x3, which is our highest order in this differential equation, it is d3. So we're gonna have 3 phase variables, is equals to the second derivative of m. So that should do it for us. Okay, so remember that our phase variables are like state variables, but since we are moving from the frequency domain to the time domain, we call them phase variables. Okay, so now we go to step 4. And step 4 is we differentiate our phase variables to get our dynamic matrix. Differentiate our phase variables. So this just means we're gonna differentiate x1, x2, and x3, and so that we can get our dynamic matrix x dot. We can remember that. So we're gonna go back to blue. So we're gonna say x1 dot is just the first derivative. It's just dm dt, and as you can see here, dm dt is x2. That's very important. And then x2 dot is just the second derivative, conveniently, of m, which is x3. And now what is x3 dot then? Does it mean it's the third derivative? Yes, it is. dt squared. And does this mean it's x4? No, it does not. We don't have an x4 here because we only have 3 state variables. So what this is our answer. Remember, at the end of step 2, I chose to rearrange this. This is our third derivative in terms of the other derivatives and the input, and that's very important. So the third derivative is just everything that's here. So I'm just gonna copy this. Let me try again. I'm gonna copy this. I think I got it right. And we're just gonna place it over here. I think it should fit. Yes, it will. And gonna clean that up, and I'm gonna create a new page so that we can work with this. So now we can take this, and what we do next is, I'm gonna use a red pen, is we can say that this one becomes, and I can move back to the blue pen because I want to express this in terms of our state variables. Minus 24m, 24m, we said up here, m is x1. So this is going to be x1 minus 26. The first derivative of m is just x2. And minus 9, second derivative is x3. And it's going to be plus u. Okay, so now we've just completed our state equation. Our state equation vectors. As you can see here, we have our dynamic vector, and here we have our state vector. So we should be done with finding our state equation, but we are not done. We still don't have the output here. And where do we find the output? If we look back on our block diagram, which is up here, our output is part of part 2. So we've only done part 1. So now we need to do part 2 the same way we were doing part 1. But let's look at this. So we're going to start with part 2. I'm just going to point out part 2. Part 2, we said it's just y of s over m of s. M of s was our intermediate function, which we get right after part 1. It's the output of part 1. So now it's the input of part 2. Okay, so y of s is equals to, no, this transfer function is equals to s squared plus 7s plus 2. Okay, so now if we start with step 1 again, which was to linearize, we get y of s is equals to m of s multiplied by s squared plus 7s plus 2. Okay, so now what we can do is we can go to step 2, where we the inverse Laplace transform. And if we take the inverse Laplace transform, what do we get? We get y of t is equals to the second derivative of m of t with respect to time plus 7 first derivative of m of t with respect to time plus 2 m of t. Okay. What does this mean? Does it, well, before we can go to step 3, and that's if we're going to have to go to step 3, let's look at this equation here. It's a differential equation, but what does it mean exactly? Do you notice that we don't have the output here, we don't have the input here, and we don't exactly have our dynamic vectors. We don't have our dynamic vectors, but what we have in effect is a full definition of our output, because y of t now is standing on its own, and there's no output here to confuse us. So this is just our output on its own. So if our output is defined by the intermediate, then it should be obvious that this is in effect the output equation. Let me make it a bit more clear. So remember up here, we defined our phase variables and the derivatives of our phase variables. So we can do the same here and say y of t, we can just simply replace the second derivative of y of t is just x3. Remember that second derivative is x3, so I can write this as x3 plus 7. The first derivative, isn't that x2? Yes, it is. It's x2. So that's x2 plus 2m, m of t was just x1. And just like that, we have our output equation. So that means we don't have to do steps 3, 4, and 5. Well, we're going to have to do 5, but it's not going to be part of part 1 or part 2. So this means that, well, we get a very important result, and that's the numerator of a transfer function in the form of P of S over R of S, hope I didn't get that in reverse, only affects the output. So that's very important, because the numerator strictly affects the output. And this is the numerator, as you can see. So we were able to separate the numerator and have it in part 2. So if we quickly scroll back up to our block diagram, this is the numerator we're working on in part 2, and it only affects the output. The denominator affects the state, and that's very important. And I think it's worth noting again here that this affects output, or we can say affects output, and this affects the state of our system. And this should be a bit more obvious when you work with root loci methods. You'll notice that we are more interested in the poles than in the zeros, as the poles affect the stability, which is the state of our system, and the output will be more affected by the zeros, which are the numerator. And this is evident with what we're doing. So are we done with our question? No, not exactly. We still have to write out our state space model now in matrix form, and that's going to be step 5. So we can say this is part 3, and part 3 is just going to have step 5, and that's write state model in matrix form. So what do? This is our matrix form. Again, I'm going to write this until everyone fully has memorized this. And y is equals to cx plus du. So you'll notice we have found our x vector, which is the state vector. We have found our dynamic vector, which is x dot. We have found our output vector, and everything else should be a bit more discernible. So now we can start with the first equation, which we call the state equation, and it should be x1, x2, x3, all derivatives. This is our dynamic vector, is equals to, we call this the controllable matrix, and it should be equals to, if you've been following here, and we're going to start with x dot 3. X dot 3 says minus 24x1 minus 26x2 minus 9x3 plus u. So it's minus 24 minus 26 minus 9. Minus 24 minus 26 minus 9. We can't lose our matrix here. Okay, and then I think for x dot 2, x2 dot, it's just x3, and x1 dot is x2. Okay, so we should know this pattern by now. That looks like that, and everything else is 0. And this one is just going to be our state vectors. x1, x2, x3. That's our state vector. plus, and this is going to be our b vector, and our b vector is just the coefficient of our inputs, and our coefficients is just 0, 0, 1 because our input is only affecting x3 dot, so that's going to be 1 and everything else is 0, and there's our input matrix. And then we have y. So now y, we pointed out that it is defined by this, and if I rearrange this properly so that we start with x1 followed by x2 then x3, we get 2x1 plus 7x2 plus x3. So the coefficients are 2, 7, and 1 in that order. Sorry about that. 2, 7, 1 in that order, and that's x1, x2, and x3. And just like that, we have fully converted our transfer function into a state space model with a minimum of fuss. So this should be the last video of this state space modeling tutorial series. I will make more videos if I feel the need to go more complex, because from here onward the methods and the concepts get a bit more complex. The purpose of this video series was to keep everything simple. If I do, I will upload them online as well, but I don't think I will be making any more videos. Until then, take care.